All right, so what we're going to start to try to do is calculate the area of a certain space under a curve, and that's represented here by this section S, which is just a section underneath this curve y equals f of x. We don't really know the equation of this function, just some generic curve. I want to know the area of this space. So there are a couple ways to do this using rectangles, and that's what we're going to start off doing, is just sort of by visualizing ways that we might be able to calculate this space. So what we could do is we could say, well, let's cut this thing up into two rectangles, and then we will calculate the areas of those rectangles, and that'll give us a pretty good estimate for the size of this space. And so what I'm going to do here is just show the visualization of what we're doing here by cutting it in half. All right, so I'm going to cut this space in half all the way up to the curve, and I'm going to turn this space to the left of that point into one rectangle. Right, so we should be able to visualize that this is all one rectangle that we could calculate the area of. I don't necessarily know what this point is here, but if I knew these distances, then I could calculate this, because I would be able to find the height of this rectangle, and I would be able to figure out what the width is of the base as well. And so if these are equal sections, then I've also got a rectangle over here that goes up to this point and comes across. All right, so now I have two rectangles. And what I could do is calculate the area of the two of those. But one thing that you're going to notice is that we've got an issue here, one being that this first rectangle over approximates this space. There's a lot of space here that I would be calculating that is not under the curve. In the meantime, over here I've got a lot of space that I need to be calculating that's unaccounted for. So this is an issue, and obviously we're not getting the exact value of what is here. We're over approximating on this half, we're under approximating on this half. So there are a number of things that we can do to try to get a more accurate representation. All right, so let's try this again. Well, rather than cutting that section up into just two pieces, what if I cut it up into four pieces? And I said that this is one piece, this is another piece, this is another piece. And remember, when I do this, I'm assuming that this distance, this distance, this distance, and this distance are all the same, so that all of my rectangles have the same base, right? So when I do this, I'm going to have a rectangle here. That one's under approximating our curve. A rectangle here, which is a slight over approximation of the curve. A rectangle here, which looks pretty close. It's under approximating and over approximating in some different spots. And then finally a fourth rectangle that's definitely under approximating. But what you'll notice about these areas that we're missing is they are smaller now. So this space is a lot smaller than the space we were missing in the previous attempt. And then this space is an over approximation, but it's a small over approximation. Here we're getting less and less area that isn't being covered or is being covered too much by these rectangles. So we're going to try to do another one of these, and I'm going to cut these up into halves as well, and you'll start to see this really come into focus. So now you can see that we've doubled again the amount of sections we've cut this space up into, and although we are over and under approximating in some different areas, it's a very small space that's getting left out or being calculated extra, right? So you could see that what we could end up doing here is by taking the areas of all of these rectangles and adding them together, and then taking the limit of these areas as this distance approaches infinity, right? As the distance between each rectangle approaches infinity, then we can get closer and closer and closer to this actual area. And right now it's just a theoretical number, right? We take that limit as it approaches infinity, that's going to get us really close, and that's going to be our best approximation right now. So we're going to draw a bunch of rectangles and calculate those areas, and then we will know approximately what the area is underneath this curve. So let's put this idea into practice, and we're not going to take a limit as it approaches infinity. We're just going to approximate an area here and recognize that it will be an over approximation or an under approximation, depending on how we cut this section up. So we're going to use rectangles to estimate the area under the parabola y equals x squared, which is drawn here, from x equals 0 to x equals 1. So here is x equals 1. One thing that we know about this function is that this point is actually a point where familiar with, that's the point 1, 1, because if I plug in 1 here, I'm going to get 1 squared. That'll be 1. All right, so I have this area defined, and what I want to do right now, just for the sake of seeing a simple example, is let's cut this space up into fourths. And I want you to do the same thing here. So we've got 1/4. That's that mark on the x-axis, right? That's exactly where that takes place. This would be 1/2. It's exactly where that is on the x-axis. And this is 3/4. And so what we're going to do with this space is create 4 rectangles and calculate their areas. So we've got one rectangle here, which looks like it might be a massive over approximation. We've got a rectangle here, which is over approximating a bit, a rectangle here, and a rectangle here. And all of these look like they are over approximating this space. What I mean by that is the area of this rectangle is much greater than the area under the curve contained within that rectangle. Because when I calculate this area, it's going to be including this space, which we don't actually want. So we know we're going to be a little bit over with this number here, but let's do this anyway. So one thing I know right now is that of all of these rectangles, this distance is 1/4. And it's important that all of these rectangles have the exact same width. But their heights are all very different. So I am going to have to calculate the heights of these rectangles if I want the area of this whole space. So we're going to calculate this, and I'm going to use R because I'm saying we're using the right boundaries here. And there are 4 rectangles. So let's see what this sum actually ends up being. So we've got our first rectangle, the first space, plus the second space, plus the third space, and the fourth space. And this is just notation. You could use any variable you want, but essentially this is what we're saying here. That these are the 4 spaces we're adding together. So how do I calculate these areas? Well, to get the first one, I'm going to take the length times the width of this rectangle, or the base times the height of this rectangle. So the base is 1/4 still, just like it is for all of them. But the height of this rectangle is dictated by however high this point is. And that point right there is the point 1/4 and then whatever f of 1/4 is. And that's the height of this rectangle. So I will need to calculate f of 1/4. Well, f of 1/4 is going to be 1/4 squared. So this is going to be times 1/4 squared. So that's the area of this first rectangle. The second rectangle also has a base of 1/4, but its height is different because that point is the point 1/2 f of 1/2. And 1/2, if I'm calculating f of 1/2, it's 1/2 squared. So this is going to be 1/4 times 1/2 squared. Plus, now I have a third rectangle which has the same base, but you're starting to pick up on the pattern here. But this time, it's the height of the point at 3/4. And finally, the fourth rectangle has a height of 1 squared. And so by adding all this up, we do assume it's going to be an over approximation, but we're going to have an actual number here. So let me clean up the math. So just to speed up the process, I've done the multiplication, I've added them all together. We would probably use a calculator here at this point, but we end up with approximately 0.46875. And that's what we are estimating this area to be. Now we know that that has to be an over approximation because of all of these areas here that we calculated that actually weren't a part of this curve. But we know that that area can't be greater than that number. So another way that we could have done this is with a left-hand approximation. And just because of the length of this video, I'm not going to put it in this one. We will do an example of a left-hand approximation tomorrow. But what I could have done instead, and I'll just draw it in yellow here, is I could have said, well, let's cut it up into the same exact slices, but this is my first rectangle here, an under approximation. And then this is my second rectangle, an under approximation. And this is my third, and then my fourth is essentially 0 here. and these would all be under approximations. So what I'd be able to see is what this number is compared to this number, and I would know that my area lies somewhere in between. And again, think about the idea that by chopping this into even more and more rectangles, we get closer and closer. But this is the idea that we're starting with these Riemann sums, is just by adding together rectangles to approximate these areas. So we will do more with this tomorrow.